Okay, so after this, I would like to come to introduce our speakers today, who is Professor Joshua Ruderman from NYU. I was fortunate enough to know Josh ever since he was a graduate student at Princeton, where he was working with Professor Nima Arkani-Hamed. After he got his PhD, Josh moved to Berkeley as a Miller Fellow and then started his faculty appointment at NYU in 2014. He's a renowned expert of physics beyond the standard model, collider physics, and dark matter physics, which is also the topic of today's talk. So his title is Dark Matter Genesis, Tales from an Agnostic. So let's welcome Professor Ruderman.
Hello, everybody. Thanks for coming. So my talk will be about dark matter with a focus on some ideas for how dark matter may have been produced in the early universe. Sorry. But first, actually, I want to begin with some sad news. We think of the Aspen Physics Center as a family, and you're all here today, so you're, at this moment, at least part of the family. So as Csaba mentioned, this is the Heinz Pagel Memorial Lecture. Heinz Pagels was a physicist from Rockefeller University who died hiking nearby on Pyramid Peak. And just 2 weeks ago, there was some more very sad news in our community. Well, two renowned theorists both died in separate outdoor accidents in the same weekend. They were both members of the center in the past. Steve Gupser was a renowned string theorist at Princeton. I was a grad student at Princeton. He was the director of graduate studies when I was there, so I knew him at that time. Ann Nelson was a particle theorist at the University of Washington. And Steve died rock climbing near Chamonix, France, and Anne died on a hike in the Cascades. I know Anne better because our research is more similar, although she's 100 times better than me. She was one of the most creative theorists in our field, but also she stood up for young people and stood up for diversity. And her and I actually worked together to plan a conference here at Aspen last winter, 2018. So it was a really good experience for me working with one of the masters to plan an event like this.
Steve grew up in Aspen.
Yeah, or in Colorado.
No, right here in Aspen.
Okay. So sorry, but I thought you would be interested. Okay. So for my talk, you may have seen this before. This pie chart shows our understanding now of the energy composition of our universe. And because E equals mc squared, when I say energy, that counts up everything. It counts mass. It counts all the stuff. And remarkably, all of ordinary matter, like protons, atoms, all of the elements of the periodic table, stars, planets, all of that fits in within 5% of this pie chart. The rest is something else. The majority is what we call dark energy. The universe is expanding, and we now know that the rate of that expansion is accelerating. So in the future, it'll be expanding faster than it is now. We call dark energy what is driving that expansion. And the simplest explanation for that was actually posited by Einstein as what we call a cosmological constant. It's some constant energy of empty space that can drive this expansion. And what we see is consistent with this simplest explanation. This talk will be about the remaining quarter, which is most of the matter. We call this dark matter. Unlike here, where we have at least a simplest explanation that works, here there's not really any consensus on what the simplest explanation is. And this talk will be about some ideas for what it could be. Okay, so that's the pie chart. And I learned a helpful way to help you remember the pie chart, which I'm stealing from Annika Peter. And I'll call this the cupcake model of our universe. And for this analogy, the cupcake is the dark energy. The icing would be the dark matter, right? That's a quarter. And then all of us and the stars and stuff would be the sprinkles. So if you forget the pie chart, just think of cupcakes. This is making me hungry. Okay, so here's my plan for this talk. I'm going to begin by telling you some of the evidence for why we think there is this dark matter in the first part. And then what I really want to get to is the third part, where I'll tell you some ideas about how dark matter may have been produced in the early universe, but those ideas are all speculative. So before I get there, I want to tell you something not speculative. So in the second part, I'll tell you about the history of the ordinary matter, the 5%, which we understand well. Okay, that's the plan. Okay, so first, evidence for dark matter. This is an image of Andromeda galaxy, which is sort of the closest big galaxy. And if you were able to go out of the Milky Way and look in, it would look something similar to this. And what can you see? Well, you see all the light that comes from all of the stars and gas. What you don't see is the interesting part. It's mostly what you don't see. We now think it's immersed in a big ball of some unknown source that's not interacting with the light. That would be the dark matter. So why do we think it's there? Well, one reason we think it's there is by studying the motion of stars within galaxies. And we see the same thing in all the galaxies that we look at. So stars orbit galaxies. Our sun is orbiting the Milky Way every few hundred million years. We do an orbit. Just from Newton's gravity, we can understand that. So this video on the left shows what you would predict a galaxy to look like if it were only made of stars and ordinary matter. And on the right, it shows what we actually see. And if you look carefully, you can see the stars are moving much faster on the right than the left. So the stars are moving much faster than we would predict if galaxies were only made of the ordinary stuff, like stars. Okay, now I'm going to show you a slightly more technical way of making the same point. This is what we call a rotation curve. And you can make a plot like this for any galaxy. So galaxy by galaxy, you can make this plot. This is an example for a galaxy M33. And the image of the galaxy is overlaid here with the plot. From left to right is the distance of stars from the center of this galaxy. And then the vertical distance on the plot shows the velocity in kilometers per second that stars are orbiting this galaxy. And then these dots show the data. So that's what we observe. And then the solid line is drawn through them. The dashed line is what you would predict from Newtonian gravity if this galaxy were only made of the stars and the gas, the ordinary matter. And you see that they're different. The stars are much faster. So that's another way of showing the same thing. This type of rotation curves, the study of these was pioneered by Vera Rubin in the 1970s. She passed away a few years ago. Myself and many of us in the field think that she should have won a Nobel Prize for this work. It was one of the most important works in fundamental physics in the 20th century, so I think that was a real oversight, establishing really the concrete evidence here. Okay, so to summarize, if you make two assumptions that I can apply regular Newtonian gravity and that galaxies are only made of ordinary matter like stars and gas, then you can make a prediction for the motion of stars, and that prediction is wrong. They're moving faster. So that must mean that one or both of these assumptions is wrong. If the first one is wrong, well, then you'd have to modify gravity in some way. If the second one is wrong, then you'd have to add extra matter. If you add extra matter, that can give more gravity and then cause stars to move faster. Just looking at galaxies, either of these could work. But when we look at other things, we see that really only number 2 works. So another source of evidence for dark matter comes from looking at clusters of galaxies. Right, so galaxies are things that are made up of, say, hundreds of billions of stars. Clusters of galaxies are one step bigger. These are things made up of many galaxies. This is an image of what we call the bullet cluster. And it's actually a merger of 2 clusters of galaxies. And if you look here, the red and the blue, this shows where the ordinary matter is located in the bullet cluster. Most of the ordinary matter in the cluster is gas that's emitting X-rays, and we can see where it is by looking at it with an X-ray telescope. So here's the ordinary matter. But then the interesting thing is if you look at these contours, the contours, these green contours show where most of the mass, most of the matter in the bullet cluster is located. We infer its location using something called gravitational lensing, which was predicted by Einstein, and it's that gravity can bend light. The more mass you have, the more gravity, the more the light bends. So by the amount light bends, you can infer both the location of mass and the amount of mass. This is sort of an artist's impression of an extreme case. It's not going to be that extreme here, but still, by looking at the lensing of more distant objects, as their light passes through the bullet cluster, we can infer where the mass is, and it's located at the center of these green contours like a topographic map. And so you can see just by looking at this that most of the mass is at a different location in the bullet cluster than the ordinary matter that's emitting the X-rays. So the ordinary matter is here, the mass is there. So just by looking at it, you can see there's something else there. It's being dominated by something else, something that is dark that's not emitting X-rays. This video shows a simulation of what we think is happening here. As these 2 clusters merge, the dark matter just passes through unperturbed. the ordinary matter experiences a violent collision, gets stripped out, and you get these shock waves. So the dark matter just passes through, ordinary matter interacts, and then you end up with something that looks like this. Now, the studies of this go back now over a decade. You shouldn't conclude too much, maybe just looking at one system. Maybe something weird happened here that we don't understand. But just in the last few years, there's been progress applying this method to a whole ensemble of systems of clusters. So here, each of these boxes is a different system of 2 or more clusters. The bullet cluster is just the one in the upper left. And in each case, lensing is used to identify mass. X-rays are used to find ordinary matter. And across this entire ensemble, we see a separation between the 2 components. So we now have very strong evidence that the bullet cluster is representative of this class of object, and that most of the matter is located in a different location than the ordinary matter. Okay. And this you wouldn't be able to explain just by modifying gravity. You really need something new here. Okay. So I'm a particle physicist. So when I wake up in the morning, I want to understand things at their smallest, most fundamental level, take them apart, understand particles. This shows our current understanding of particles, the standard model of particle physics, which was developed in the 1960s, and these physicists won the Nobel Prize in '79. It has 3 types of particles, and all of physics that we see on Earth can be explained by this relatively small number of particles. So there are quarks. Quarks are what make up protons and neutrons that are at the center of atoms. There are leptons, including the electron that makes up electricity, heavier cousins of it, neutrinos, which I'll talk about more later. And there are force carriers that are responsible for forces. So here's the photon. That's what makes up light, and it is responsible for the electric and magnetic forces. The other 3 are responsible for nuclear forces. There was a missing ingredient, as I show the standard model here. We didn't understand how to explain the masses of these particles. This missing ingredient was discovered a couple of years ago at the Large Hadron Collider at CERN, the Higgs boson, which explains their masses. So it's actually a 4th type of particle. It was discovered in 2012, leading to the Nobel Prize in 2013. Now, today I'm going to focus on dark matter, so I'm not going to go more into the particle physics. But if you're interested to learn more, I'd like to advertise actually next week's lecture, same time in this room. And it's by Chaba, who introduced me. And he's going to talk more about the standard model. It's going to be amazing, much better than this. So come next week. And he's going to talk about the future, well, not only what we've learned at the LHC, but what we could learn with future colliders. OK. So back to dark matter. We want to understand what particle can explain it. That particle must have a few properties to explain what we see. First, it should be dark. It should not interact with light, so it should not have an electric charge. Okay, second, it should be long-lived. In general, particles can be long-lived. So the electron and the proton, as far as we can tell, they're definitely longer lived than the age of the universe, and we've never seen any, as far as we can tell, infinitely long-lived. Some particles, though, they decay quickly to other particles. Like the Higgs boson decays much faster than a second to other particles. So the dark matter has to be of the first type, long-lived, because it was produced billions of years ago in the Big Bang, and it's present now. So it should be a long-lived particle. And number 3, it should have the property that it clumps into galaxies in the early universe, since we see it in galaxies now. And well, it turns out that although some of the standard model particles have some of these properties, there's no particle that has all of these properties. So we cannot explain the dark matter with any of the known particles of the standard model. It requires something new. Okay, so here's the standard model again. We need to augment it by adding some new particle that can explain the dark matter. As a particle physicist, this is very exciting to me because it's a very sharp problem. There's this stuff out there. What is it made of? Let's figure it out. Once we figure it out, we'll presumably award another Nobel Prize. I don't know when that'll happen, but I've optimistically put a 2 as the first digit. Okay. So I've told you basically what we know. We know how much of it there is. We know that it's dark, but there's a lot we don't know. So what do we not? Okay, what is it? And by which I mean what type of particle makes it up, and what are the properties of that particle? For example, what's the mass of that particle? What are its interactions? Where does it come from? By which I mean how was it produced in the early universe? So we come from a Big Bang event 13.8 billion years ago. that event should have produced the dark matter that we see in the universe today. How did that happen? What is its story? Or we would say, what is its cosmology? Okay, number 3, how complicated is it? We only know how much there is, so we don't, is it just one thing? One simple particle that makes it all up? Or maybe it's 10 different types of particles that add together to give the amount of dark matter we see. Ordinary matter is very complicated. You have all the different elements of the periodic table. It can clump into planets and stars, and it can be in gas. So is dark matter very simple, or does it have a lot of structure? That we don't know. Okay? So I've told you that it's 25% of the energy of the universe, but a more practical question that you might have is how much is here? Well, so let's look at the Milky Way. Okay, it's really a picture of Andromeda, but let's pretend it's the Milky Way. So it's a spiral galaxy. The stars extend out about 50,000 light years. And we think that each galaxy is immersed in a much larger ball of dark matter. That's what you need to explain the motion of the stars. It's bigger than the location of the stars. So for the Milky Way, it would be something like 300,000 light years, and it would be sort of a big sphere, a big ball full of dark matter. And you could ask how much is here in our neighborhood in the solar system. And there should be about 1/3 of a proton mass per cubic centimeter here, say, in this room. So for example, if the dark matter has a mass 100 times the mass of a proton, which would be a reasonable guess, although we don't know its mass, but if that were the mass, then in every 10 centimeter cube box, there would be 3 of them here in this room right now. So there should be some here, not too many. No, I thought I saw one, but no. Okay. But still, this 1/3 proton mass per cubic centimeter makes a lot of sense to a physicist. It might sound a little abstract to you. But happily, I saw a kind of a neat way to explain this in an online cartoon that appeared last week on a webcomic called XKCD. And actually, somebody who was considering coming here emailed this to me. I don't know if they're here. Oh, thank you. So dark matter is 0.3 GeV per centimeter cube. That GeV is about the mass of a proton. So when I said 1/3 of a proton, that's the same thing. Okay, and then the cartoon says that's equivalent, if you add it up over the Earth, to a squirrel. That doesn't sound like a lot because a squirrel is a lot smaller than the Earth. But most of the Milky Way is empty space. So if you added up a squirrel per Earth volume over the whole Milky Way, that would be more mass than all the stars. Now, so I'm a physicist, so I was trained to be very skeptical. And if anybody ever tells me something, my first instinct is to think it's wrong or to check it myself. That's sort of how we're trained. So we should check if this comic is correct, right? So let's check it together. Okay, so here's the Earth. If we want to add up the mass of dark matter in the Earth, we should take the density and multiply by the volume of the Earth. Okay, so the Earth has a radius of about 4,000 miles. The volume of a sphere is 4 pi over 3 radius cubed. So that's an elementary geometry fact. My preferred way of doing this calculation is with Google. So the Google search window can be used actually as a calculator, you may not know. So not only look for websites, you can calculate. And it actually knows what centimeter means. It knows what the proton mass is. It knows what the radius of the Earth is. So I plug this in, 1/3 proton mass per centimeter cubed. That's the density. 4 pi over 3 radius of Earth cubed in pounds, say. So Google says 1.3 pounds. Okay, cool. You could try this at home. So this, for a physicist, this was the easy part. The hard part is to check what a squirrel is, because I'm not a biologist. So I looked online. A type of squirrel here in Colorado is the fox squirrel. So I looked it up on Wikipedia, and they say the mass is 1 to 2 pounds. So it checks out. So I think the cartoon checks. Okay. So I told you 2 sources of evidence for dark matter: the motion of stars within galaxies and clusters of galaxies. And I want to emphasize that in both cases, the evidence relies entirely on dark matter's gravitational interactions. Okay? In the first case, dark matter sources gravity that pulls stars faster. In the second case, dark matter leads to gravitational lensing. And all we know so far is evidence for it from gravity. And that's not surprising. We say gravity is universal. It acts on everything. All types of particles must feel gravity. Dark matter must feel gravity. But the problem is that doesn't tell us much. So we know its total amount, but we don't know more. So for those of us working on the dark matter problem, the sort of holy grail right now in the field would be to learn something about its non-gravitational interactions. This would allow us to zoom in on its particle properties. So for example, electricity and magnetism is a non-gravitational interaction of ordinary matter. It doesn't act on dark matter, but there may be other things that act on dark matter, and if we can find those, we will learn a lot. So that's really the big practical goal of those of us working on dark matter. Okay, so I want to pause and take a break from dark matter and now tell you about what we've learned about the history of ordinary matter, and then I'll come back to dark matter and tell you some speculative ideas for where dark matter may come from. So for the next part of the talk, I'm going to tell you about the cosmology of ordinary matter from the Big Bang 13.8 billion years ago till eventually formed stars till now. I'm going to break this down a bit. Okay, so the key fact about cosmology is that it was discovered by Edwin Hubble in 1929, and it's that the universe is expanding. And Hubble discovered this by observing that distant galaxies are moving away from us. The further they are from us, the faster they're moving away. This can be explained if the universe is expanding and empty space is being created everywhere that's pushing them away from us. So as the universe gets older, it's getting bigger. If you were to look at it in the future, it would be bigger than it is now. The universe also has a temperature, and as it gets bigger, it's getting colder. So if we were to look at it in the future, it would be both bigger and colder than it is now. And the kind of key idea for cosmology, if we want to understand the past, we should just think backwards in time. Okay? So that if we think backwards in time, if it's growing and getting colder now than in the past, it should have been smaller and hotter. So the kind of key to understanding the properties of the universe right after the Big Bang is to understand the properties of matter at very high temperatures. So before I tell you about the sequence of events that we think happened after the Big Bang, I first want to tell you how matter would act at very high temperatures, and that'll kind of give us the ingredient we need to understand this. So for the next part of the talk, I'm going to do what we in physics call a thought experiment, which means something that you in principle could do, but you probably don't want to, or it's probably hard to do. In this thought experiment, you're definitely not going to want to do in real life, but we can still think of what will happen if I take some stuff and heat it up. So I'm going to take a box, and I want to fill it with just some empty space. So go far away from any star or galaxy, grab some empty space. Empty space is not nothing. There's stuff everywhere. If I grab some empty space, it's going to have some photons that make up light passing through. So I'm representing them by these green squiggles. It's going to have some small amount of atoms. Even in the middle of empty space, there's going to be some small amount of atoms. The temperature of this empty space in our universe today is 2.7 Kelvin. That's the unit of temperature we like in physics. You can convert that to Celsius by subtracting 273. For Fahrenheit, use Google. But this would be about 1% of room temperature, very cold. So there's some atoms. An atom would be a proton orbited by an electron. If there's just one proton, we call it hydrogen. So there's some. Here's a more complicated atom. This has 2 protons and 2 neutrons. That's helium. It would have 2 electrons around it. Now one key property of this box of empty space that we grabbed today is that the photons can freely move through it. It's transparent. That's why we can see stars and galaxies. Space is transparent to light. Okay. So now what I want to do is heat it up. So how am I going to heat it up? Well, of course, I'll use a Bunsen burner, like in high school chemistry. Okay, now let's just wait. It gets hotter. Okay, so something interesting will happen when the temperature is 3,000 Kelvin. That would be the temperature of the surface of some stars. And what's going to happen is that these atoms just fall apart. At this temperature, the electrons fall out of the atoms, and you no longer have atoms. You just have a bath with some protons and some electrons, but the electrons are no longer attached to the atoms. So before, the electrons are attached to atoms, and now the atoms fall apart. We call a gas like this a plasma once the electrons are no longer stuck to protons. This plasma is opaque. Light cannot pass through it, so you can no longer see through the box once we've heated it into the plasma stage. Okay, now I'm going to heat it more. The hotter I get, the weirder things are going to be from our everyday experience. Okay, so keep the Bunsen burner on. Okay, so when I get to 1 billion Kelvin, that's a bit hotter than the center of a thermonuclear bomb explosion. And what happens at this temperature is that you initiate nuclear processes. These are going to be processes that change one type of element into another. So for example, helium can change into 4 hydrogen. just by taking apart the protons. So my heliums break. Okay? And now I'm going to make it even a bit hotter still, and it's going to get even weirder. Okay? So at 500 billion Kelvin, which is very hot, something cool happens. You create a large amount of antimatter. So we are all made of matter. We're made of protons. There's a corresponding particle called an antiproton that makes up antimatter. If you bring together matter and antimatter, they will annihilate each other and explode. Fortunately, there's no antimatter around here now. But if you make this box 500 billion Kelvin, it'll actually become full of antimatter. And now it's sort of a bath of matter and antimatter. It's this plasma. It's opaque. OK. So yeah, you wouldn't want to do this experiment at home. OK, so to summarize, we grabbed some empty space far away from any star in the universe today. It's at 1% room temperature. It's full of atoms. It's transparent. We heat it up. First, it becomes a plasma that's opaque to light. Then you trigger nuclear reactions, sort of like a nuclear bomb. And then eventually you reach a high enough temperature that it's full of a soup of both matter and antimatter. So that's what would happen if you heated up some stuff. And now we can understand the cosmology just by running our thought experiment backwards, right? Because the universe started very hot. So it did start in this condition, and it cools to what we see here. So just take the same thought experiment, run it backwards, and then you can understand cosmology. So let me go through those steps now, but it's going to use the same ingredients. OK, so I'm going to begin less than 1 millisecond after the Big Bang. And it's hot enough that the universe is full of a combination of matter and antimatter. So I have both protons and antiprotons in my box. There's going to be slightly more protons than antiprotons. For every 30 billion for every 30 million antiprotons, there'll be 30 million and 1 protons. So finding that extra proton would be like finding one person in Shanghai. But it's going to be very important. In a moment, you'll see that there's slightly more matter than antimatter. Okay, if you wait a little bit, at say around 1 millisecond, the matter and antimatter find each other and annihilate. Boom. And now the antimatter is all gone once you cool, or once the time is longer than about a millisecond. And now that's why it's important that there was slightly more matter than antimatter. It all annihilates until you're just left with the extra matter. And that's why we have matter today and not antimatter. Okay? If we wait a little longer, say 3 minutes, we're now at the temperature where the entire universe is acting like a big nuclear reactor. You can process hydrogen into heavier elements. So, for example, we can form some helium. And in fact, we can calculate the properties of this nuclear reactor in the first few minutes. And it matches the abundance of elements we see in the universe today. And that's a key way that we know that this story I'm telling you is correct. OK, so then let's wait even longer. And when you reach a few 100,000 years, you cool down to be as cold as the surface of a star today. And now it's cold enough that electrons can fall onto the protons, and you can form the first atoms. So when the universe is a few 100,000 years old, the first atoms are born. When it's hotter, they are just destroyed. At this moment, the universe becomes transparent. So remember, in our thought experiment, the box began transparent before it was a plasma. So when the universe is a few 100,000 years old, you form the first atoms. The light can move. It becomes transparent. The light from that moment we can see today. And we call this the cosmic microwave background. So it's the first moment we can see, because before this moment, it was a plasma and opaque. But when the universe reached a few 100,000 years old, it became transparent, and light from that moment we can see today. So this is an image of it from the Planck satellite. The red and blue parts show you where it's slightly hotter or colder. So this cosmic microwave background was discovered serendipitously in 1964 at Bell Labs by Penzias and Wilson. They were not setting out to measure this because they didn't know about it. They were trying to build a very good radio microwave antenna. And then they noticed that they saw what they thought was a constant noise in all directions. So they thought something was wrong with the antenna. They tried to figure out all sources of noise. One source that they were worried about is they noticed that there were pigeons nesting in the antenna, and they thought the pigeon poop could be the noise. So they used, this is the actual trap they used, which I think you can see in the Smithsonian. They caught the pigeons, drove them to some other town in New Jersey, let them out. So what did the pigeons do? They obviously flew back to their nest. So then they used a more drastic method. I wish I could say that no animals were harmed when this experiment was performed, but I can't. Okay, but anyway, big success for science. Okay, so a few 100,000 years, again, first atoms form, and then if you wait till today, that would be 13.8 billion years after the events I just described. You cool down to this 2.7 Kelvin that we are now, and it's nice and cold in space. So to summarize, right within the first millisecond, you have this bath of matter and antimatter. All the antimatter annihilates and goes away. Then you have nuclear reactions that produce elements that we see today. The first atoms are formed. You get the CMB. Then now. Okay. So that's sort of a rapid introduction to cosmology and the history of ordinary matter. Kind of heroes of my field arrived at this understanding over decades of work. But I want to emphasize that everything I just said is only about that 5% of the pie. So this was a history of the ordinary matter, the atoms, the light. We don't know what is the history of actually most of the matter, the 25% of the energy that makes up the dark matter. Does it have a similar story to what I just described, or does it have a completely different story? We don't know. Okay. So back to dark matter. For the rest of the talk, I'm going to tell you several ideas for what the history of dark matter could have been in the moments after the Big Bang. Okay. Now we don't know the dark matter mass. We just know the total amount. If the mass is larger, then you need a smaller number to get the same amount of mass. If the mass per particle is smaller, there should be a larger number. But just for example, if we take the dark matter mass to be 100 times the proton mass, which would be a good guess, then you could ask how much dark matter is there today. So one way of answering that was a squirrel per Earth. Another way to answer that question is to compare the number of dark matter particles to the number of photons that make up the cosmic microwave background. And it turns out you don't need much. So with this mass, there would be about 30 dark matter particles per trillion photons in the CMB to explain the amount of energy we see now. So there are many photons per dark matter now in the universe. And now we could ask, what did it look like in the moments after the Big Bang? Well, in fact, if dark matter has sizable non-gravitational interactions, then we would predict right after the Big Bang there should be a lot of it. There should be roughly the same number of photons and dark matter. All the different types of particles would have about the same amount. So there should be about the same amount of dark matter and photons and protons right after the Big Bang. So if you want to explain the amount of dark matter we see today, the problem is not how do you get enough of it, it's actually how do you deplete it down to the amount we see now. If you still had as much dark matter as photons with this mass, there'd be way too much dark matter now. So the different ideas I'm going to tell you for how dark matter might have been produced really boils down to how do I go from the situation on the right, where you have a comparable amount of dark matter and photons right after the Big Bang, to the situation we see now with many more photons than dark matter. Okay, and I'm going to tell you 3 different stories for how that might have happened. So naively, you might think, since we physicists don't know what dark matter is, you might think that we don't know how to explain it. That is absolutely not the case. We have the opposite problem. We know how to explain it several different ways, and we don't know which of these ways is true, if any of them. So it's not hard for us to explain it. The hard thing is to tell which explanation is right. So I'm now going to give you a few different examples. Each of these examples could be right. Or who knows, if it's made up of multiple different constituents, maybe there are even multiple stories for the different constituents. Okay. So first, I'm going to tell you about an idea we call the weakly interacting massive particle, WIMP. And this has really been the community favorite that's received the most attention. There are thousands of papers written by physicists about WIMPs, both theorists and experimentalists. So the idea of the WIMP is the idea that dark matter interacts with ordinary matter through a type of interaction we call weak interactions. And I'm going to now tell you how that fits in to this standard model of particle physics that Csaba will tell you more about next week. But here's the particles of the standard model. I want to focus here now on the particles that communicate forces. The photon, shown by this Greek gamma, is the particle that makes up light, and it communicates electric and magnetic forces. There's a particle that we call the gluon. This communicates the strong nuclear force. This is the force that binds quarks together inside protons and neutrons. Well, the other two we call the W and the Z, and these communicate what we call the weak nuclear force. this is a force that's, for example, is responsible for certain radioactive decays that we observe in elements. And the idea would be that dark matter just interacts with us through the weak nuclear force. And we already have examples of particles that only interact with us through the weak nuclear force. And this would be the neutrinos over here in this part. And in fact, neutrinos are constantly being produced by the sun. Through the nuclear reactions in the sun are constantly producing neutrinos. And there are a lot of them actually passing through this room right now. In every square centimeter, if you point it at the sun, then there would be about 100 billion neutrinos per second passing, say, through your thumb. If neutrinos interacted through electricity and magnetism, you'd be pulverized instantly. So fortunately, they don't. Since they only interact through this weak nuclear force, it's very rare that a neutrino would interact at all. Our bodies are just transparent to them, and they're just passing through unnoticed. You need very special sensitive detectors to see them at all, but we are constantly bombarded with a sea of them from the sun. The idea for WIMP would be that it also interacts with us through these weak interactions. And I told you we need to figure out how to get rid of it after the Big Bang to bring it down to the small amount relative to the number of photons we see today. The dark matter can be removed through a process we call annihilations. In the early universe, the dark matter is bouncing around, and sometimes two dark matter particles will collide with each other. And then they can annihilate, which means that they're destroyed. They're gone. And then you can convert their energy into, say, ordinary particles like these W and Z particles that communicate the weak nuclear force. So that would be an example of an annihilation, where two dark matter particles find each other, are destroyed, make two ordinary particles. So now if we think of the universe, so here I'll take a little box to show some piece of the universe. And right after the Big Bang, it's full of many dark matter particles. Each circle here will represent one dark matter particle. They're bouncing around. Sometimes they'll randomly hit each other and annihilate, and then be destroyed and converted into ordinary particles like these W and Z force carriers. And then the density of dark matter dilutes as this process occurs until you reach a small enough density that the dark matter particles are unlikely to find each other. And then the density of dark matter particles stops being depleted, and then we'll match what we see today. So you start with a lot, they annihilate, and then you're down with a smaller amount that matches what we see today. So the process that the cosmological story here is using are these annihilations into ordinary matter. If dark matter can annihilate into ordinary matter, then it can also scatter against ordinary matter, and that's something we can take advantage of with experiments where we can try to look for it. So it could be that a dark matter particle comes along, hits, say, a proton. It could scatter it and give some energy to the proton, and that we can try to look for. So we call experiments that look for this direct detection experiments. So we build sensitive detectors full of ordinary matter. We make it very clean and sensitive. We put it deep underground where it's quiet, and we would look for a dark matter particle once in a while coming in, scattering, depositing some energy that we can look for. Experiments of this type are now done throughout the world. In the United States, a leading site for this is called the Sanford Underground Research Facility. So this is the deepest United States science lab in South Dakota. So experiments like I just described are in this lab. It's very expensive to build underground facilities. I wish that physics had that much money, but in practice, we piggyback off of underground facilities that are built for other reasons. This Sanford Underground Research Facility is in the former Homestake Mine, which this is a picture of it in 1889. It was, I think, America's largest gold mine, and it ran until about 2002. And now it's a physics lab. There's a little fun bit of American history here. Actually, not long before this picture was taken, the gold was first discovered in the Black Hills of South Dakota in 1874 by an Army expedition led by George Armstrong Custer. He was a Civil War hero, but he's most famous for what happened 2 years later when he died at the Battle of Little Bighorn. So he led this expedition. Actually, this is a picture of him on the expedition with a grizzly bear he shot. They discovered large deposits of gold in the Black Hills. After that, they displaced Native Americans from the Black Hills onto reservations. They weren't happy about this. And the Battle of Little Bighorn was 2 years later, and Custer died. So there's an indirect connection between dark matter searches today and Custer's last stand. Okay, so this shows the status right now of these experiments. So on this plot, from left to right is the mass of each dark matter particle, which is unknown. So if you posit a model, then you would pick a location here. So if it were 100, if each dark matter particle had 100 times the proton mass, you would live here. Okay, and then vertically, this shows the strength of the dark matter interaction against protons. For these WIMP models, you would expect the strength to be somewhere in this range, and the mass to be somewhere in this range. And different models really can populate this whole plane. So the WIMP is not very predictive in terms of its location in this plane. There are different versions of the WIMP that could live at different parts here. The blue region is excluded by the type of experiments I just described. If dark matter had a mass and interaction strength in the blue region, you would see energy being deposited into these experiments at a higher rate than is seen. So the experiments are too quiet for dark matter to live here. And this fact already excludes many models of the WIMP, but there are also models of the WIMP that would live in the white region. So the white region would be fine. Now the red region here is where it's going to be hard, because if dark matter has a mass and an interaction strength that would put it within the red region, you would have more events in these experiments from neutrinos that are here than from dark matter. And then it's going to be very hard to find dark matter, because you'd have to somehow separate it from the neutrino events, and that's hard. So if dark matter lives in the red region, it's going to be very hard, or perhaps impossible, to find it with this type of experiment. So we hope that it lives in the white region. There are interesting models of WIMPs that live in this region. For example, if dark matter interacts with the recently discovered Higgs boson, that would generate an interaction with protons that's in this region here. And this dashed line shows projections for upcoming experiments that could happen in the next few years, some of them in this Sanford facility I mentioned. If dark matter lives in the white region above these purple curves, then we will discover it in the next few years. And in my opinion, that's actually one of the most exciting experimental things happening in the next few years in fundamental physics. So you should keep an eye out. It could, at any time, you could see a New York Times article that one of these experiments discovered it. Or it could live below the purple line, and then we won't see it, or it could live in the red region, and we might never see it. So either are possible. We don't know. Okay. So that's the WIMP. And this is the idea that's received the most attention from our community. And WIMP is, there are many versions of the WIMP that are excluded, for example, by the experiments I just described, but there are also versions of the WIMP that are still fine that you wouldn't have seen yet. So the idea is still viable. However, it could have been seen already, and a lot of us are worried that it might not be true. So a lot of the field now is thinking about ideas for dark matter beyond the WIMP. And I'll now describe an example of that we call hidden sector dark matter. So in particle physics, we sometimes talk about sectors of particles. And what we mean by a sector of particles is a group of particles that have mutual interactions. So here I show the different particles of the standard model. And then the blue lines show, if there's a blue line connecting two particles, that means that they have some interaction. So like the neutrinos have weak interactions. So there's a line connecting them to the W and Z, for example. The electron has electromagnetic interactions. So there's a line connecting it to the photon. But all these lines connect. So we would call this whole group of particles in the standard model a sector. We could call this the ordinary sector. All the stuff we know about, it all interacts. In this language, the WIMP that I was just describing would be the idea that you add the dark matter particle to our sector of particles by connecting it to the weak interactions. So you draw that line there, and then you'd say it's sort of part of the same sector in a sense. But it's possible that dark matter doesn't interact through the weak interactions, so we can break that line. Dark matter might not be part of our sector of interacting particles. It might not interact with us except through gravity, which is very weak. So it could be that dark matter is part of its own sector, and in this case, we would call this a hidden sector, and this would be a group of particles that doesn't interact with us except through gravity. Everything interacts through gravity, but if it doesn't interact in any other way besides gravity, we would call it a hidden sector. So dark matter could be in a different sector. There could be other particles in that sector that interact with dark matter, sort of in parallel to what we've seen with ordinary matter. For example, there could be a dark photon that interacts with dark matter. So just as our photon generates the electric and magnetic forces, there could be a dark photon that doesn't generate our electric and magnetic forces, but some parallel version that only operates on dark matter and not us. So we would call that a dark photon. There could be more complicated things in there. In general, if everything interacts through gravity, if we only interact through the hidden sector through gravity, then I would just call it like this. But there could be some weak interactions beyond gravity. We would call this a portal, and that might be present or it might not. So there might be some weak interactions, or there might not. Okay. So if dark matter interacts with the hidden sector, then dark matter could annihilate into hidden sector particles, and that could be a different way of depleting dark matter in the early universe that may have nothing to do with the weak interactions. So that's how this can be different than the WIMP. In this framework, I could start with two dark matter particles if they find each other and annihilate, whereas before they annihilated into ordinary particles, in this dark sector, hidden sector, they could annihilate, for example, into dark photons. And then this process now has nothing to do with ordinary particles that we know about, but it's still a way of depleting dark matter after the Big Bang. So the story would be similar to before. We start with a lot of dark matter after the Big Bang, and occasionally dark matter particles will find each other and annihilate. But in this case, they're annihilating into hidden sector particles and not into ordinary particles. But otherwise, it's the same story as the WIMP. You annihilate until the density is small enough that they no longer find each other. So everything I said before, just replace annihilation into ordinary particle, like W and Z, into annihilation into dark particle. Otherwise, it's the same. But then, well, this, of course, necessitates no interaction with us, and that means it might be harder to see it in experiments. So in this framework, you might be lucky and see it in direct detection. If there's some portal interaction between the sectors that is strong enough, then you might be able to see it. But you very easily might not see it if the two sectors are too weakly coupled to each other. So if the interactions between our sector and the dark sector are too feeble, then very easily in this direct detection plane I showed, the interaction strength with proton can go down to the unobservable level below the plot. So you could still see it in direct detection if it's in a hidden sector, but you might not. You sort of have to be lucky to. So this sort of allows for an easy explanation of why we haven't seen it yet in these types of experiments underground, if it is in this dark sector, hidden sector. Even if dark matter does not interact with ordinary matter by a sizable amount, we can still learn about non-gravitational interactions of dark matter. For example, dark matter may have large non-gravitational interactions with itself. It might bounce against itself. So it could be that through hidden sector interactions, you might have situations where two dark matter particles collide and are not destroyed, but just bounce. So we call this a self-interaction. That this could be generated in these hidden sector models. So it bounces against itself. This cannot happen too much, or else the bullet cluster wouldn't look the way it looks. I told you the way we understand this is that the two clusters pass through each other. The dark matter is unperturbed. The ordinary matter interacts and is stripped out, giving these shock waves. If dark matter interacted as much as ordinary matter, you would also see the dark matter would also be stripped out. So the dark matter interaction should be weaker or more rare than ordinary matter interactions, but they could still be present. And there's now a big effort trying to figure out ways to look for their effects by studying the properties of galaxies or clusters of galaxies. Galaxies will look different depending on whether dark matter particles can scatter against each other or cannot scatter against each other. So this is a way that we can learn about dark matter's interactions that doesn't actually require it to scatter against ordinary matter. So maybe we can't see it in direct detection. Maybe we can infer its properties from looking at the shapes of galaxies, for example, and seeing whether the scattering is happening. Okay. I have one more story for you. Oh, that should say a 3. That we call asymmetric dark matter. And this story is going to crucially involve antimatter. So let me just take a quick antimatter interlude. All particles have what we call antiparticles. We've already seen an example in this lecture that there are protons and antiprotons. So the antiparticle of the proton is the antiproton. The antiparticle of the electron is the positron. If you bring together the matter and antimatter, they annihilate and destroy each other. So both the proton and the electron have distinct antiparticles that are different from the proton and the electron and can destroy it when brought into contact. However, some particles do not have a different antiparticle. In this case, we say that the particle is its own antiparticle. That just means that there's no different antiparticle. So for the proton and electron, there's a different antiparticle, antiproton, positron. Examples where there's no different antiparticle would be the photon or the Higgs boson. So there's no antiphoton, there's no anti-Higgs boson. So in this situation, we just say that they're their own antiparticle. So there's two possibilities in general. A particle could either have a different antiparticle, or a particle could be its own antiparticle. we don't know which of these two types of particles dark matter is. So it could be that dark matter has a distinct different antiparticle. There could be a dark matter particle and a dark matter antiparticle. Or it might not, and there might just be the dark matter particle, and then we would say the dark matter is its own antiparticle. So both of those are possible presently. If dark matter does have a distinct antiparticle, then there's another story for how it could have been generated after the Big Bang that I'll now describe. And the idea is just to mimic the story for protons and antiprotons. So just to remind you, we began in the early universe in that first millisecond with a bath of both protons and antiprotons, slightly more protons, one person per Shanghai. The triangles pointing up will be protons, the triangles pointing down will be antiprotons, and whenever the matter-antimatter meet, they'll annihilate and be destroyed, and then eventually all the antimatter is gone, and you're just left over with the extra matter. That explains the amount of protons we see now. It could be, if dark matter has a distinct anti-dark matter particle, the exact same story might also apply to dark matter. This idea we call asymmetric dark matter. So the idea would be that you begin after the Big Bang with a bath of both dark matter particles and dark matter antiparticles, represented by upward and downward pointing triangles. And when the dark matter particles and antiparticles find each other, they annihilate and are destroyed. And then eventually you're left with no dark matter antiparticles, and then you just have dark matter particles, and that could explain the number of dark matter particles we see today. In both cases, there were slightly more protons initially than antiprotons. There were slightly more dark matter than anti-dark matter initially. So we say that there's an asymmetry in the number of protons and antiprotons, or the number of dark matter and anti-dark matter. So we call this idea asymmetric dark matter. And it's quite reasonable because we've already seen that this is what happens to protons. So we already know that this definitely happens to ordinary matter. Maybe it also happens to dark matter. Okay. So the amount of protons and the amount of dark matter in this case is set by initial asymmetry. Okay. So I've told you now 3 stories for how dark matter could have been produced immediately after the Big Bang. The first one is sort of our community favorite, the WIMP, where it annihilates through the weak interactions, the same interactions that neutrinos interact with us through, and that removes it in the early universe. In the second case, dark matter does not interact through the weak interactions, but it has its own interactions, and it annihilates into hidden sector particles in the early universe. Okay, and in the third case, there's dark matter particles and antiparticles, and there being slightly more dark matter particles is what set the number you see. I want to emphasize that the 3 ideas I just told you are only the tip of the iceberg. Our community has had a lot of ideas for what dark matter could be, and even just in the last few years, there are a lot of new ideas. So these are representative ideas. But we really are in a brainstorming stage still of this problem, where we're still just trying to think of what are the possible ways to explain it. Different stories for how dark matter was produced in the early universe can point to different experimental tests as being promising today. So I highlighted direct detection as a promising way to look for WIMPs. In the case of hidden sector dark matter, another way to look for it could be looking for the self-interactions. So by thinking about how dark matter was produced, that can change sort of how we think about what experiments we want to build to look for it. But really the problem, as I said, is that we can explain it multiple ways. We really need to figure out which way is right, and we're going to need data to do that. So we need experiments. We need more data to differentiate among different possible stories. So I've already highlighted direct detection. This is where dark matter scatters against ordinary matter, and we read it off that energy deposition in the sensitive detector. Another way that we can look for dark matter is through annihilations that happen in the universe today. So I told you the dark matter annihilations can explain the amount of dark matter we see, but those were annihilations that happened right in the moments after the Big Bang. If it annihilated in the early universe, it can also annihilate today. In only a very small fraction would annihilate today, but you could still look for the effects of that. So for example, 2 dark matter particles in the Milky Way today could find each other, annihilate, and make ordinary matter. This shows one way we would look for that. This is the sky as viewed with gamma rays, which are the highest energy photons that we measure with a satellite called the Fermi satellite. And it could be that dark matter annihilations in the Milky Way today produce these gamma rays that could be detected by a satellite like Fermi. So that's one of the ways. So that's sort of a complementary way to direct detection that we're looking for dark matter today. would be, for example, looking for injection of gamma rays. A third way that we look for dark matter is alchemy. We try to make it. And if dark matter interacts with ordinary matter, then you should, in high energy conditions, be able to make it. And we're trying to do this in colliders like the Large Hadron Collider in CERN at the border of Switzerland and France, where we collide protons at very high energies. And it could be that sometimes when you collide two protons, you might produce dark matter particles. We don't know if that happens or not. If dark matter interacts enough with protons, then that should happen. If it interacts too weakly, it won't happen. But this is something we're actively looking for at the Large Hadron Collider, would be evidence for production of dark matter there. So those are three different experimental paths, looking for it depositing energy by scattering, looking for the effects of its annihilations, or making it through alchemy. And well, the more data are coming, and hopefully we'll get some evidence for its non-gravitational interactions, and that can help us point towards what story might explain its origin after the Big Bang. Okay, so I'd like to end with an analogy. I'm from New York. This is a famous cover of the New Yorker magazine from 1976 that you may have seen. And I can tell you, as a New Yorker, this is an accurate representation of how New Yorkers view the universe. So here you're on 9th Avenue, you're looking west, there's 10th Avenue, the Hudson, Jersey, if you ever want to go there, and then like eventually there's some mountains and the Pacific Ocean and some other countries. But really, New York is the center of the universe that matters, right? So the analogy, there might be an analogy to how our community has so far approached the dark matter problem. We've spent a lot of effort on one possibility, the WIMP. It's a very compelling idea theoretically. It takes advantage of interactions that exist, the weak interactions. It could be the dark matter interacts with us through that way. And I want to emphasize WIMPs are still viable. We very easily could have seen it already, and many versions are now excluded, but there are still versions that are allowed. However, we're beginning to explore the fact that there's really a much bigger space of possibilities for what dark matter could be. So I'll say that the ideas beyond WIMP could be, say, America beyond New York City. And well, so the name of this talk was Dark Matter Genesis Tales from an Agnostic, so I'm agnostic. So if you ask me to bet, my true belief is that there's even things we haven't thought of yet, which could be, say, other countries in this analogy. So I'm betting on what we haven't thought of yet. Thank you.
Thank you very much, Josh, for this very nice lecture, and we have time for a few questions.
Yeah, and before the questions start, I just want to advertise that there's going to be square dancing after the questions. So here's a slide advertisement for that, but now I'll take questions.
Okay, questions, yes.
So after you reduce all of the dark matter down by any of those models, right, what happens to the energy that was carried by that dark matter originally?
Good question. Yeah, in the WIMP case, it goes into the ordinary matter. So there's a bath of ordinary matter, photons and electrons and protons, and the energy just gets put there, and then that's fine. Yeah, in the case of the hidden sector, it's being deposited into the hidden sector, and therefore it's a good question because we have powerful constraints, for example, from studying the cosmic microwave background on the amount of extra energy there can be in the universe, and there can't be that much. So you need to arrange the model either to put the energy back into the ordinary sector or to have not too much in the hidden sector. And there are future experiments that will look at the cosmic microwave background more precisely that could detect if there's some energy stored in hidden sector particles, and that is another avenue for looking for dark matter.
Along the same lines, the word annihilation is just a tool, right? I mean, there's no such thing as annihilation. Correct? I mean, it turns into something else.
Sure, but
Steam turns into
by annihilation, I just mean that it's gone and turns to something else, and this
turns to something else.
is something we do routinely in particle physics experiments. So for example, if you bring electron and positron together, they are gone and can convert into photons, into high energy photons. So then we say that,
That was like his concept is it's got to go somewhere.
yeah, indeed, very important. So
And there is a dark energy theory, and you've probably already explained that, but as to what ordinary things turn into, and that the word is energy, therefore, there's a good chance dark matter, dark matter as well as dark energy is that process of the annihilation.
Yeah, so
So-called annihilation.
So a very important, so you're right, a very important principle in physics is conservation of energy. So through this annihilation, particles can be removed like dark matter, but the energy is still conserved, and then it needs to go into something. And that's kind of key behind why I needed to use something like the weak interactions or interactions into the hidden sector, is that the energy that was in the dark matter must go into something indeed.
I didn't catch the reason that you attached to the fact that there used to be, at the time of the Big Bang, way more dark matter particles than there would be now. You said they had to equal the number of photons.
Yeah.
The reasoning behind that.
If dark matter has sizable non-gravitational interactions with other particles like ordinary matter, then it'll be produced in the early universe in large numbers. So it's a good question. I told you dark matter can annihilate into ordinary particles, but in the early universe, the opposite process can happen. Ordinary particles can produce dark matter. So at high temperatures, if you have sizable interactions, you will automatically produce a large amount of dark matter, and you'll have a comparable amount of dark matter to the number of photons. So it's just the opposite process of the annihilation. You can take ordinary matter and then make dark matter. This will happen with a large rate right after the Big Bang. So it's a good question. Thank you.
And the expansion of space. Dark energy causes space to expand, which in turn causes more dark energy to happen. Is this dark energy coming from dark matter? In which case, dark matter will be reducing as time moves on, and dark energy will be increasing, which if it goes backwards, then at the time of the Big Bang instant, we would have like 100% dark matter and 0% dark energy. Are all of these indications correct, or on the money, or what?
The simplest explanation for dark energy would be what we call a cosmological constant, that there's some constant energy of space. If that is the explanation, then it's really separate from dark matter. There's some constant energy of space, but otherwise the dark matter is something else. And that's why in my talk I didn't mention dark energy past the pie chart in the beginning. If it's a cosmological constant, it's a separate concept from the dark matter that can be separated.
Is it believed that dark matter affects either the velocity or trajectory of gravitational waves?
That's an interesting question. In principle, it could. I don't think it is for the ones that we're seeing now at LIGO. But just as light experiences gravitational lensing, gravitational waves would too.
So it's a question of numbers.
Indeed, you need enough mass.
Over there.
Under the influence of gravity, hydrogen can aggregate and form stars ultimately, and neutrons can aggregate and form neutron stars. It doesn't seem like dark matter aggregates like normal matter does. Is that any kind of a clue to what dark matter could be, or the properties that it must have, such that it won't aggregate?
Yeah, that's a
to the extent that normal matter does.
so that's an interesting question, and indeed, it depends on the model. In principle, in the simplest versions that I described, dark matter would not collapse into structures in the same way that ordinary matter does. But if you add interactions to dark matter, you can have it collapse. So it could be that dark matter collapses into some structures. But it must be the case in galaxies that although the ordinary matter is in a disk, the dark matter is consistent with being in a big ball. So it can't collapse in the same way as ordinary matter. But still, there are various possibilities. It could be that a subset of the dark matter, say 10% of it, collapses into its own disk. That, in fact, would still be OK. And the other 90% is a ball. It could also be that pieces collapse into objects, but that it's still a ball in the galaxy, but made up of collapsed objects. So there really are a couple of possibilities.
One last one.
Not have been detected if indeed it does clump to that extent?
It can't clump too much, but in fact, that's something that we're trying to look for now. So for example, there's a satellite called Gaia that's measuring very precisely the motion of billions of stars, and it could be that we could detect dark matter clumps by studying carefully the motion of stars. That's something people are actively looking for now. So based on current data, it can't clump too much, but it could still clump a little, and we're looking.
Last question over here.
So if the primary evidence for dark matter is gravitational interaction is primarily curvature of space-time. What's to say that there's just not an odd property of space-time, maybe related to curvature, dimensional curvatures out of string theory, which are kind of odd. That just space-time is weird and there's no particles at all. It's just
Indeed. So, the first piece of evidence I told you was the motion of stars within galaxies. And that, in principle, could be explained either by adding more matter or maybe by modifying gravity in some way. But it's very hard to imagine how you would produce things like the bullet cluster just by modifying gravity, because you see that most of the lensing is happening in a region distinct from where the ordinary matter is. So if you only had ordinary matter and gravity, even if you change gravity in some way, it's hard to see how you would produce things like the bullet cluster. So when you take all the evidence together, it's all beautifully consistent with adding another particle. It's hard to imagine how you would change gravity, but people do think about that. So that's a hard, but it is a path that people pursue.